Hi everyone.
Hello, Hitesh.
Yeah, hi.
Yeah, Hitesh. Yeah. Welcome, Hitesh. Um, I think we can start the Hitesh. Welcome, Hitesh Burman. He is a computer science background engineer, and he is one of the member of Ladakh Science Foundation. And today he'll be covering the programming concepts those programming concepts you can use it while designing the robotic robots or drone or whatever. So I welcome Hitesh. Please continue with your presentation.
Yep, sure. Hi everyone. Uh, Welcome to the first uh, uh, set of sessions on programming. So I'm Hrishikesh. I think I have a slide on me as well, but I wanted to have this session in a very approachable way. You don't need a computer or anything. You just and I think this session is supposed to last 1 hour, but I won't take that much of your time. I think there are like maximum about 10 slides. And as I go over each of the slides, you can ask me about any questions that you have. This has to be like something very casual kind of, right? And there will be subsequent sessions where we will be talking about like intro to programming, those kind of stuff things. Those will be much more practical, where I would expect you to like pay much more attention to what is actually happening on screen. But this session is more like, okay, how do I think about programming? What are the ways I should approach? Okay, I have a problem. How do I start thinking about something? Okay, that is the background of this session. Uh, all right, I will start. And is so if you are using the chat, if you you can hear me well, if the audio and everything is well, can you put a thumbs up on the chat? Thumbs up or any emojis will help. Yeah, great. Thanks, Akarma. We'll start. Okay. First of all, who am I? I'm a hobbyist developer. I was a software engineer. I worked for a while and then I quit my job. And then I'm right now just doing multiple projects, the things that I want to build. So I am like as a programmer, you are using your programming skills to solve problems. But usually those problems that you get are given to you by someone else. You are solving someone else's problem, but the ability of programming, the ability that you can make a machine, make a computer do something, that is a amazing ability. And I felt like rather than trying to solve others problems, I wanted to solve problems that I face or problems that my community faces, something like that. So yeah, so that was my past, and right now I'm just doing hobbyist programming, and I'm also interested in education research. I'm doing education research, and I like making things. I like animals, sunshine, note taking, and science, of course, right? So that's about me. That's the most I will speak about myself. Then what is this? And I think I summarized what this session will be about just in the first slide as well. But for the sake of this slide, a short and incomplete summary of thinking in general. How do we think? Why do we think? How does our brain work? The way it works, that kind of stuff. And like even uh, to summarize computational thinking in in such a short session, it's somewhat hard. And also the idea of computational thinking is very vague. So it's almost you have to be there doing it. It's hard to explain. So I have a like interactive session in this slide as well. In couple slides down, uh, we'll have that. So also, why do we even need to learn about thinking? You have been thinking for so long, right? You've been thinking since the day you were born. Like something was going in your mind. You were crying. You were crying because something you felt something did not like, and then you had emotions and everything, right? But there is a way to approach problems. If you see a problem, for now, when you drive a car, when you walk, when you run, you have something going in your mind ki I'm running, and your body responds to those movements in that way. So like knowing this, these things have become second nature to you. But as you approach unknown problems, what do you do? So there are ways you can approach unknown problems. Even if you don't know, you can solve it. That is the main idea around computational thinking. If you get a problem that you have never seen before, you can figure out, you can think about that problem in ways, you can try to fit that problem in different ways which will make more sense. Suppose I think that I think a lot of school students do it. If we get a problem, mathematical problem, we draw it out on paper. When we draw it out on paper, it makes much more sense than the question being in the question paper, just like in English. So you just translated English into diagrams, and just by the translation, that thing makes more sense to you, right? Okay, I'll go to the next slide. So so far, I just wanted to have one more rounds of thumbs up if so far everything is making sense. Okay, okay, I'll continue. Yeah. Yeah, this is again, I already explained it on the first slide. Goals and exploitation. Think about thinking, understand different kinds of thinking, understand how computational thinking, and I don't want any prior programming experience on this. And this is information that you already know. It's just you being aware of your thinking, right? Next. So uh, let's I want you to do an activity here, right? But before doing our activity, we'll do like proper introduction to thinking. So like just by looking at the slide, I'll just read it out. Thinking means concentrating on one thing long enough to develop an idea about it, not learning other people's ideas or memorizing a body of information. However, much of that may be useful. So if you think about, if you have never been to Delhi, so I went to Ladakh for the first time last year. So before going to Ladakh and before actually having an idea of that place by me visiting that place directly, I had an idea in my mind, and that idea was given to me through media and other places, right? So when I was there, I could see, okay, this is the reality is. So similar to that, like if you have anything you think of, so if you have that idea that is given to you by someone else, that is you just memorizing and revisiting that memory. If you think about, if you think about Pythagoras theorem, so then you are just revisiting that memory that you have about that problem. You are not really thinking, right? And if you like, that is fine, that is not cheating. That's okay. We humans need memory, and memory is an important thing to have. Without memory, like we would have nothing. But when we talk about thinking here in computational thinking sense, we want to think about problems that we don't know solutions to, and we think about that problem so hard that we get a solution. And by so hard, we will get to know there are certain ways, certain approaches that we can take that will break down the problem into things that we can tackle individually. Right. So I want, so I'll see if so I'll see if the activity goes on. So uh, so the activity is I'll try to hack your brain. Okay. If my hacking is successful, let me know with a high five or thumbs up or something in the chat. And sorry, absolutely sorry about my video being off. So my computer had a problem. I am not able to speak from my computer. I'm talking from my phone, and screen sharing is happening from my computer. So apologies for that. Anyway, we'll go with the activity. The activity is hacking your brain. So I will say something. So my this is my claim. My claim is I'll say something, and the picture of that thing, it will appear in your head. So I'll start. Duck, truck, mountains, rivers. So I think whenever I say those words, those four words, the picture, even if you did not want to have those pictures, the pictures appeared in your brain. So there is this thinking, there are these thoughts that automatically gets triggered in your brain. So we want to be aware of how these things come in, how can we make use of these thoughts, right? So why I mentioned that activity was because that relates to so many things about thinking. So, like, there is this entire industry around thinking. Okay, we have mathematical thinking, we have scientific thinking, algorithmic, analytic, critical, traditional, creative, mental models, design thinking. So half of these are buzzwords. People use these things just to sound smart, and this thing, and some of these are useful. So when you think of computational thinking, when you think of algorithmic thinking, they're sort of mixed up together. Some people will say computational thinking, that will mean something else, and somebody else will say computational thinking, that will mean something else. So you want to be very careful about when you use these words, right? So right now I want to go to this little directory, if you will. It's called untools. So this is like tools for better thinking. So there are again different ways to structure how you think about some problem. Systems thinking, decision making, there are ways you make decisions. So there is a one very popular one that is called ooda OODA loop. So you observe something, and then you reorient, and then you decide what to do, and then you act. That kind of stuff. So there are lots of ways, there is something called Bloom's taxonomy. So Bloom's taxonomy is like, okay, how do we learn so right now this is so Bloom taxonomy is just one example of structured thinking. There are a lot of ways. One of the why I picked Bloom taxonomy is because like it specifies itself into educational realm. So whenever I am teaching something, so this is the uh, uh, graph, if you will. So at the bottom, whenever you are learning something, anything new, suppose for if you are learning about computational thinking or thinking in general for the first time ever. So right now we are at the knowledge level, right? And maybe we will touch a little bit of comprehension. Okay. But maybe some people might also do some application of the things that we are talking about today. But then comes the more extreme parts. So you will take what I am saying, and then you will be very critical of it. Oh, Rishikesh is not speaking things that are right. Rishikesh is speaking whatever is not. I don't agree with him. Then, like when you are thinking something like that, then you are analyzing that thing, and then you are synthesizing. You are like mixing that information with something else, and then there's evaluation where you can like execute that information on like some broader sense and things like that. So this is one model of thinking. So, and it doesn't have to be this way. So you, if you like, you can say that okay, Bloom's taxonomy itself is wrong. I think there should be another step in learning. That is also fine. This is so. These are just people naming different uh, group schools of thoughts into something, right? So I wanted to have this slide and dump all this information to you, just so you know कि computational thinking is not something very novel. Computational thinking is not something, oh, this is a very like very specific way of thinking. These things are very mushed up together. But but when we usually talk of like classically, if you Google on computational thinking and that kind of stuff, then you will get something around things that computer scientists use, uh, where we use computers to solve problem. We will get to that in next 2 3 slides. So next slide. So I wanted to have another slide about first principle thinking and critical thinking, right? So I can, so there is one question for you. uh, I can explain this slide, first principle thinking and critical thinking, and then go into design thinking and computational thinking, right? Otherwise, I can go to design thinking and computational thinking and then come back to first principle thinking. Which one would you prefer? Uh, can you, like, if you prefer me going over first principle thinking first, then you can comment with one. If you want to go me over design thinking and computational thinking first, then you can comment two. I will take votes from the chat. I'll wait for your votes. Padma is saying one, design thinking. So we have a 50-50. I'll do a final, the third one. Okay. So we have three votes. We'll go with one then. Sorry, Mifam. Next time I will definitely take your choice. Oh, we have we have four. Mm, ठीक है. I think we have a tie here. Uh, okay. Okay. We Heather broke the tie. It's design thinking. Sure. Okay. No more votes closed. Oh, votes closed. Sorry, Sakarma. Votes closed. Sorry. Okay. Uh, we'll go with design thinking, and then we'll come back to first principles thinking. ठीक है. Design thinking. So when I was preparing this slide, so when I was preparing this slide, I myself was confused about okay. So because I am not, so I'm a programmer, I am more trained in computational thinking and that kind of stuff, and I have heard about design thinking a lot of my friends talk about design thinking, but I never bothered to really look into it, right? I never bothered to okay, what is this, because like I said, these things, when you work on any problem, you are at the same time, if I go back to this slide, if you work on any problem, you are almost always doing all of these things together. You are by traditional thinking, you, I mean, like, your culture has some impact on your thinking, right? So even though if you are thinking something very technically, because of your culture, there will be some biases introduced to your thinking. Those things will be there, right? So at any point of the time you are trying to solve a problem, you are doing all these things simultaneously, right? So like I probably have used design thinking in my approaches in probably, but I did not really deep dive into it. So like I read up on it, I summarized this for myself, I understood this myself, but like in if I have to summarize it one way, like that is think like a designer. So what I mean think like a designer. So designers, when you design something, you design in a thinking what who will finally use it. So if you are designing a car, you the first thing you probably have to think is like who will be driving that car. I mean, if that car is supposed to be driven by 3-year-old kids, then you cannot have the distance between the clutch and the seat much, right? It has to be so small. If you want that car to be driven by dogs or cats, then it has to be totally different. If you are designing that for human, it has to be totally different. So you need to think about the end user. So design thinking is very much focused around end user. And the and this term design thinking is not just not did not appear organically. So there was this thing in Stanford University, the professors and everything. So they tried to come up with a conceptualized idea about, okay, these are the things that we need to take care of. What do we call? We need to like put a term to this kind of thinking where we are designing a product and we need to think about the users. We need to develop processes and systems around it. So what do we call this term? So that's how the term design thinking came up. So there is this example on the screen, as you can see. uh, uh, what do you think? Is this a good design or is this a bad design? This is the Apple Magic Mouse. I think the newer version don't have this. This was one of the older version. So what do you think? Is this a good design or bad design? Or like do you have any thoughts around it? What do you observe when do you see this? You can put it in the comment. Mipam says bad design. I think it's because you are going to use the mouse and then like the cable is right there. Anyone else? By the way, I will give you one more context here. This is a wireless mouse. When I say this is a wireless mouse, does that change anything? Stanzin thinks it's a good design. Stanzin, I think either says it's average design. I think you can unmute yourself and also speak if you want. If you want to like be more critical about, okay, I think this is bad design because I think this is good design because. If anyone wants to open their mic and speak, you can speak. Okay, I think people are hesitant about opening their mic, but uh, we'll see that about in uh, the offline sessions. Everyone has to speak then. Anyway, so yeah, so this is I personally feel so. This is like if it was so again, really has to do with what who is the final user. So I hinted ki this is a wireless mouse, and like there is this more what do you call it, explanation about why it is the way it is. So this is on the next slide. So this is from someone just explaining some doing some explanation about why it is. So it is a wireless mouse. So when you are actually using it, you won't be using the cable. And 5 minutes of charging gives you 10 hours of usage. So maybe like it's probably not as bad as it looks, but it could have been better. So we can always be thinking about what is the use case, who is the user. So they have probably thought, whoever designed it, they have probably thought, okay, these are our users, these are wireless users, and we want to put aesthetics above the usability in certain cases. So even though we see, okay, this is a bad design, straight off, like who will put a cable right there when when you can put it the other way. So whatever this is, they did some kind of a design thinking with which they concluded ki okay, even if we put this there, it should be fine. So there is always some kind of rationale, and that thinking itself can result in bad outcome and good outcome. The outcome is what we are saying, but I wanted to give this example because because it has a very critical edge to it. It shows uh, after so much, because Apple has good designers, right? It has one of the best designers in the world, and after having all those designers, they decided to do something like that. So what could have gone through their mind to design a product like this, right? uh, okay, so now we'll come to computational thinking. uh, I think we have an activity here now. So yeah. So what is computational thinking? Oh, by the way, so far, if everything is going good, so sorry, because this is a Zoom session, right? So I find it very difficult to gauge if like I am interacting with the people. So if everything good, you can like put another thumbs up. I'll just wait for 1 second, 2 second. I'll wait for yeah. Thanks, Kunjis. And by the way, I'm extremely sorry if I am pronouncing people's name wrong. Like I'll get your names in the offline sessions properly. Thank you, everyone. Okay, I'll go with the computational thinking. So, so the idea of computational thinking is breaking down. That's, if I have to summarize computational thinking into one word, that would be breaking down. So like I'll just read out whatever is in the slide for the sake of the slide. Break down complicated problems into something easier. Then I have three big sounding words: abstractions, processes, simulations. After that, think about the problem more deeply and more carefully. Think about the invariance. Again, big word, invariant. And then finally, think like a computer scientist. So I'll explain these three lines quickly. So first one is self-explain. It's simple. We have a big problem. So think of it like this: you have a big stone. You have a big stone, and you are told to, okay, you have to break this stone down. You have to like make it into very small pieces, right? You have a big stone, and then you are given a hammer. So what will you do? You like, it depends on the material of the stone, of course. If it is a different material, with one hit it will scatter. But suppose it's like the typical stone, mountain stone that we get, like you have to hit it. So if you want to make it very small, you hit it, it will break into two, and then you tackle with the half of it, and then you half of it, then half of it will break into four quadrants, and then you deal with the individual thing, right? So that way you solve the bigger problem. The main task is break this big stone into many small pieces. So how you dealt with that is you broke that down into two pieces, and then you like dealt with the two other pieces. That's the breakdown thing you did. But uh, but then, by doing this, you did the same thing again and again, right? You broke down, and you broke down again on the broken down pieces. So you did some kind of a process. You did the same process repeatedly again and again to achieve the same results. So that explains the middle one here. So that is, you create processes around it, and then you create abstractions around it. So there is this. So first the problem was, convert this stone into smaller stone. So then you have an abstraction around it. Okay, we will break it. There is this abstraction of breaking, which, so when you say breaking, it doesn't have any idea, okay, if it is a big stone or small stone. So you abstracted it. So you say the abstraction to solving that problem of breaking a big stone into converting a big stone into smaller stone is breaking. The abstraction is breaking. And then you can apply that abstraction in even to a bigger stone, and to a smaller stone as well, right? You are applying that abstraction at multiple levels. But that abstraction might not work with something like wood. So if you have that abstraction, you're saying, okay, someone gives you a big block of wood and says, okay, break this wood into smaller pieces of wood. And you then if you try to apply that same abstraction there, it will not work, right? So then you again have to have a higher view, look at the problem deeply, analyze. Then you have to do some analytical thinking. Okay, what is this material? Does hammer even work in this material? And then you think back, then you break it down again. And for that, the simulation thing, right? So then you can do like there is simulation, as in like you can before doing the actual thing, you try to do it in a way that simulates the real thing, but it gives you more realistic results. So if you can somehow simulate that abstraction among different materials, so you started that abstraction of breaking, you implemented that abstraction of breaking into wood, you implement that abstraction on stone, and then you tried it on marble, and then you tried it on something else. So you can simulate that abstraction over multiple materials, right? And then you realize ki, okay, this is working on wood, this is sorry, this is working on stone, this is not working on wood. So with this doing simulations, you can like tell ki, okay, this abstraction works on this kind of things. So you can like generalize the computational process method that you have developed of breaking that stone, right? Then yeah, then why is this useful? Why computational thinking is useful, that is the third point. So when you think about a problem computationally, you can think about it in different ways. So you can like you can maybe sometimes we think about problems emotionally. Sometimes you won't go for a walk because go for a run because you are feeling lazy. So then you are like your mind is very emotional about it. But then if you are thinking about something, okay, I really want to be getting healthy and stuff, then you are like thinking very optimistically about yourself. So that way it changes how we approach the that particular moment, right? If you were feeling very lazy, you will be laying down, but if you are thinking in an optimistic manner, that will move your body and you will do something else, right? So similarly, if you apply computational thinking to a problem, so at the moment you have a problem, and you could think about it in any general sense, but you can also think about in a computational way. When you use computational thinking, what you will be doing is you will be adding constraints to it, because uh, like this is not generally true, but computational thinking is done by computers. And I wanted to include a slide about what are computers and stuff, but that would be too long. I mean, not okay, computers is a machine. In a more deep sense, I wanted to have a slide, but I forgot to add that slide, but we'll probably have it some other time. But anyway, but when I say computational thinking, you are thinking in computation that a computer can run. By computer, I mean physical thing that have motherboard, CPU, that kind of stuff. This can run numbers, calculators essentially, right? So then you have to think about, okay, I cannot put so much load on my computer. This is what my computers can do. Suppose before 2022, before when ChatGPT and everything was not there, you could not think, okay, I will ask my computer, hey, how are you doing? It will just respond as if it is a human. So you did not have that kind of expectations from a computer, right? So so you knew the limitations of computers. Similarly, that so again that is AI part, but in any sense you know the limit of a computer, what you can program, what you cannot program, what a computer can do, uh, how you can model a problem, like what is the limits. So you will put limits, you will think more carefully about the problem, you will not just think uh, not scientifically and that kind of stuff, right? So yeah, now we will be doing one activity, and for this we'll have if you want, you can get pen and paper if you have around you. So it's a very simple activity. So but there is time for it, and the time is 30 seconds, right? I have not explained the activity yet. So what you have to do is uh, so before I explain you what you have to do, it is this will take you through the process of computational thinking. So, like I said, what I'm going to explain is nothing new. You already knew this. So, I'm just going to name what you already knew. So you were like, okay, मैं तो ये जानता ही था. I already knew this. So, but now you have a name for that. That's it, right? So these are some new words here: decompose, pattern matching, abstraction, and algorithm. We will explain it after like the activity. So the activity is I want you to tell me without using a calculator. Like think of it as if you are doing it for the like first time you are just given this problem that way. So I want you to count from 1 to 200, or even 0 to 200, and like the addition of the first 200 number. You have like 30 seconds to do this, approach this problem. I'll wait. And I also would want to know how you approach the problem. Why did you take the approach? So yeah, I will start. I think let's start now. I'll put a timer. Mm, 30 seconds start. 0 to 200. Sum. You can comment your answers if you have your answers. Okay. I think we are done. Was anyone able to solve it? Yeah, me from did. Anyone else? Okay, Mifam, if you don't mind, let me know if you prefer to be on mute. That is also fine. If you don't mind, you can unmute and tell what approach you used.
Sir, first, how do I explain? First, I take even numbers. So, and after that, I take over odd numbers. So first, I'm I make now some numbers, into 10 and 10. So means if 5 plus 5 is 10. So I 2 plus 3 is 2. 1 plus 2 is equal to 3, and 3 plus 4 is equal to 7. So I make this
Go on. From what I understand, you just you thought like you split it up and then you sum it back, something like that. I think their mic is not working. Okay, no problem. Thank you, Mifam. So I will. Anybody else wants to give it another try? Okay, guess not. So I will have this in a open a different thing. Yeah. Uh, can you see my screen now?
Yes, sir.
Yeah, cool. I'll just quickly explain this slide because I think we have 15 minutes remaining. So the activity was counting from 0 to 200, and doing so, we will go through the process of computational thinking, which is we already do. We will just give it a name for that, right? So 0 to 200, right? So I'll just write this decompose pattern matching abstraction algorithm. Decompose pattern matching. Then what was there? Abstraction and algorithm. These are our four horsemen, right? So when I say decompose, right? So when I say, hey, friends, let's add 0 to 200 within 30 minutes. Sorry, 30 seconds. That's like if you never approached that problem before. So like if you have like some primary school math, then you already know it's the arithmetic sum formula, n by 2, n plus 1, that one, right? But this, we are not trying to use this formula here. I mean, we are, but doing so, it's like if you realize this pattern right here, right? So if you see, okay, he's telling me to add all these numbers together, he immediately see this thing and he will pattern match that thing. Okay, this falls into this formula, and I'll directly apply this formula and I'll have this answer. But then you are not like if you know how it works, then it's fine. But if you are just applying the formula, then you are not really thinking about how to solve the problem. You are just giving an answer. There is a difference between giving an answer and solving a problem. And when we want to solve a problem, we want to apply computational thinking. So when we are applying computational thinking, it will go like these steps. And again, when we talk about these steps and things, these are very controversial, if you will. So people will say, okay, no, I don't agree with this. This might be different, but like we will follow this form, right? So first thing, decompose. So we will decompose this big problem into smaller problems. So here is what we have. So 0, 1, 2, 3, right? Dot, 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 dot. Then here I'll have 200, 199. Sorry, not 0. 198. So we'll skip 0 because 0 won't have any value, right? So now we'll add 201, right? That comes up to, so again, sorry. So if you look into this, this is the decomposition of this. So this goes back to the thing that I described initially. You have a problem in your question paper, and then you draw a diagram of it, and then it makes sense. So you have this problem, you have this bigger problem. Then you try to like see it in a different perspective. So this is the perspective I put it out. So I decompose it, I spread it out, right? Like 200 to here 1. This is all that we have. Then we try to find some pattern in it, right? That is where we do pattern. So if we see, okay, what does this actually need? I want to sum all of these things, right? So now if you see, we have here, I'll take another color. We have here 201. Both of these would sum up to 201, right? If you add 199 and 2, it will also sum up to 201. So So at each step, we are dividing the whole thing. So if this whole thing by half, right? So like doing this many times, this will result into 100 times of 201. So that becomes, so yeah, I want to pause here a bit. So this is what we figured out. Uh, so if there is any confusion, please feel free to put it in chat. I will be happy to re-explain deep deeper and those things. Yeah. So this is 100 times of 201, right? So now what we figured out here is right here when we did this pattern matching, right? This is 201, 200, this thing. Then we developed a certain abstraction around it, right? So we understood key, okay, this is what we have to do. Like as soon as we get the repetitive thing, right? We were able to like answer this like uh, now that we know this is 100 times this, then we have this formula. This apparently is just this formula, right? So we can do 100 into 201, which is 20100, which is what MIFAM responded. And this is the same as if we do and 200 by 2, 201, which comes to 100. And this is the same formula, 20100. So we came to this abstraction, this formula, through approaching decomposition and abstraction. And this this whole step that we did to come up till here, this is the algorithm that we followed, right? So basically that's it. Coming back to the slide now, I think we will again go over the slide and read out these things. Uh, Tell me if this makes sense, right? Break down a problem into smaller pieces. So you had that big problem, you broke it down into, you spread it out, okay? And then pattern matching, find similarities between things. You found, okay, we had 201, 201, 1992, 201. This seems similar, right? So then you like figure out, and this is a very simplified version. In real world, when you are actually writing code, you will probably do pattern matching across books, across domains, across other things. Maybe you'll have to find solve a different problem to find the pattern. That can be a secondary thing, and that itself, so like solving another problem to find a pattern is again a pattern, right? So like this is a very simplified use case. Like when you will be doing real things, like of course things will be like more complicated than this. Then there's this abstraction, pulling out specific differences to make one solution work for multiple problems. So once you have this, you like summarize this thing into this n by 2 thing, right? This formula, predict sum. So you abstracted it. So you will be able to do this for any sum, right? And then like the whole step that you follow through, that becomes the algorithm, right? So far is everything good? Like two thumbs up, I will assume things are good. Yeah, great. Thanks, Akarma. And yeah, I'll come to this. But before that, I promised Heather, I promised Jigmat, I promised Padma to come back to this slide of first principle thinking. So I will quickly explain this. Okay. So how many of you, I mean, yeah, sorry, that would be a very wrong question to ask. I'm sure you have heard about Elon Musk, the big billionaire, right? So Elon Musk talks about one specific things again and again. If you like look at his YouTube videos and stuff, you'll be like, okay, apply first principles thinking. So you just Google or YouTube Elon Musk first principle thinking, you'll find very motivational videos, that kind of stuff there. Yeah. Not a big fan of motivational videos personally, but sometimes they're good. But yeah. So yeah, first principles. So again, the concept that Elon Musk talks about is that might not be like the textbook definition of first principles. Like everything else about thinking, these things are very vague, and this domain branches out from philosophy, psychology, those kind of things. So like these are not like pure. This will never be purely defined. That kind of stuff. So again, so we'll go with the first principle definition that I agree with, and then once you read 2 3 books or whatever, then you like say, okay, what Rishikesh told about first principle thinking is wrong. That is totally fine. We can debate on it. Not a problem. Happy to debate. But let's go with what I think first principle thinking is. So what first principle thinking for me is, we start with the truth, and this also works for engineering problems and like anything that you are trying to solve, right? So you basically keep on asking why. You keep on asking why at multiple levels. So suppose I'm feeling very tired in the morning, right? I'm not feeling I'm feeling very thirsty and everything, right? So then I'm feeling very thirsty, and that's a problem for me, right? So what can I do? I can just be there with the problem and then worry about the problem, or I can do something to solve the problem. So if I just apply some thing, then I will, okay, why am I feeling so tired? Maybe I did not drink water. And why did I? So then it's fine. Why did I not drink water? Then we'll be like, okay, my water tank got empty. Why did my water tank got empty? Because there was no rain for the last couple of days, and there is no groundwater. So why is there no groundwater? The nearby apartments, they were building this many buildings and everything got the water, and now we don't have any water to live. Why are there so many new apartments? So you get the idea, right? We can keep on asking the why thing. So basically, you get to the last why. You get to the ultimate truth by asking why. You get to the main thing, and then you start from there. So that is what I think first principle thinking is in any problem. So that way you get to the root cause. This is very similar to root cause analysis, if you heard of that thing. Again, these terms, root cause analysis, these things, all these things, I think we will get in this untools.co website. These are basically ways to structure thinking, that kind of stuff. Again, so this is very useful. I find it very useful when solving like business problems and those kind of things. So it really gives you certain insights. So and then we have critical thinking, which is similar to first principles thinking. That's why I wanted to have this slide, because a lot of people I have seen confuse first principles thinking with critical thinking. So usually with first principle thinking, you have something that is really tangible and that kind of stuff. You want to solve a problem. With critical thinking, usually it is applied while solving problems and stuff, for sure, but it is more applied in social senses. And the thing about thinking is, so it very much like mashes up social and sciences. So like I wanted to have this slide as well. So when you are thinking critically, you have to have a fear. Not necessarily, but usually you would have. So if you have a belief that like let's talk about this certain set of people who think earth is flat earthers. So if someone is a flat earther, and then they want to like test their biases, so they have a fear ki, okay, I might be wrong, the earth might not be flat, right? So which is which is true. So so here they have a assumption that they made, and then they try to verify that assumption. And even if what the result is not true, even if they don't agree with the result, they still go there, try to do the result. This is especially true when you are debugging programs in like when programming. So what happens is when you encounter, so like So I just wanted to have another round of questions. So have any of you have programmed before, like written code, Python, C, any programming language? Have anyone done it? So if you have done it, you can tell me yes, yes, no, something like that. No, sir. Sakarma haven't. Okay. Mifam has done some HTML. Yeah. So, okay, I will assume there is no programming experience here then. Yes. Yeah. Hyder has done C++. Great. So, what happens when you do like it can be HTML, it can be C++, whatever, wherever you code. So when you are doing some code, there are certain things that will happen that will not make your code do what you want your code to do. Suppose you want your code to print your name, and then it will print your dog's name. Like, why is this printing my dog's name, right? So then you have to do some kind of critical thinking about the problem. Then even if you want it to correctly print your dog's name, then you have to really think about, okay, maybe there's something wrong with the print function. Maybe it's the print function itself is wrong rather than the input that I'm providing. So you have to think at multiple levels. So that kind of thing. So this critical thinking is useful there as well. So and we will have like proper sessions in lab, and we think about these things. And I think the introductory programming sessions are tomorrow and day after tomorrow, if I'm not wrong. We will have like more hands-on things with those. So yeah, that is about this slide. And I think I have two more slides. Real quickly, I think we have 1 minute left. I think we have three slides left. We'll quickly wrap it up. Uh, I'll share the link to this slide in the WhatsApp group, so you can have look at this slide as well. Not a problem. So this is one great book. I'll in fact probably carry this book with myself when I go to lab. So this you can download. This is a very old book. I think this is from the 70s or something. So this book is so useful to understand computational thinking. And the origin of the word computational thinking was 2008, but the idea has been forever, right? So the term computational thinking was not on the internet till 2008 or something, because some this journalist come computer scientist called Wing, she published a paper around computational thinking. Okay, okay, this is what computation is. She sort of turned a coin in a way, right? Before that, the idea still existed, but the term was not there. So I think this book really summarizes the approach that computational thinking needs. So, but this, like, I have written a summary of this book right here. So basically, what it tells is this is very similar to this activity that we did, but it's just in a different form. So the thing is, understand the problem. We have a problem, really understand it. Like, don't even think about the solution. If you have a problem, don't think about the solution. Understand the problem. What is the problem actually, right? Like, really, really hard. Just think about the problem and then devise a plan. So how do you devise a plan? That is what is in this section. If you cannot, so this really goes into that breakdown thing. I'll just read it out. If you cannot solve the proposed problem, try to solve some related problem first. Could you imagine a more accessible related problem, a more general problem, a more special problem, an analogous problem? Could you solve part of a problem? These kind of things are like super apparent when you are doing real world programming, when you will be doing embedded programming, or even if you are doing web dev, you are doing embedded dev systems, whatever. So these are things you have to do regularly. So if you like code, even you don't have to be a software engineer writing code. You can be a aeronautical engineer writing code. You can be a chemical engineer writing code. Doesn't matter whichever domain you are writing code or not writing code, like whatever problem you're solving, this approach will help you. And like, again, this approach I'm pretty sure you already know. So but this, through this session, I'm just trying to give you a more structured way. So next time you face this problem, you will think, you will not miss some things. You will, okay, maybe I forgot to do the devise a plan phase, and I'm directly carrying out the plan. So suppose you forgot to devise a plan, you understood a problem and you did not plan about how to execute it, and then you are directly executed it. So then it's not working properly. So then you are like, okay, maybe I should take some time and devise a plan properly. That kind of stuff, right? And looking back is always helpful. Once you do the thing, then you understand it better. Look back at it, like next time it happens. Like looking back also like gives you flaws that could have been, right? So that's that. And this is the last slide. So this is about computational sciences versus computer science. So computational thinking is uh, I remember I put here, think like a computer scientist, computational thinking, but not necessarily. It can be, computational thinking can be used outside programming, and computational thinking is useful in many other domains. So when you think about computer science, if you look into people teaching computer science, learning computer science, these people will be talking of these things: architecture, programming languages, sorry, what happened, yeah, data processing, communication protocol, networking, the internet, this kind of things, and like formal logic and that kind of things. These things are like very computer science specific things, right? And then computational sciences, these are like using computational thinking, simulation, and this kind of thinking in other sciences. It can be mechanical, chemical, biology, whatever. So there are some examples here: image analysis. Suppose like you are analyzing some uh, like animals, you are trying to identify variants of animals or variants of birds. This can be voice analysis, whatever, particle dynamics, ray tracing, propagation, climate modeling. All these things are not very, like, these are not things that software engineer would generally do, right? But other sciences, other domains need these things. So this is where you need to introduce some kind of programming, some kind of simulations, where you need to think about these problems in a very computational thinking manner, because you have to model this real world phenomena into a computer. So then you also have to, if you want to model this in a computer, you have to know how the computer would work. If you push this button, what will happen? I think Amog was taking 3D modeling sessions. So if you click on the scale size, thinking it will change the color, that will not happen, right? So you have to also understand how the computer works, right? That is that. And what else can we discuss? So I wanted to like I could like expand this session long, but I'm really a very passionate note taker. So we could also like later when we have another session, like you can tell me, okay, let's talk about this. So I'll be happy to talk about. So we can talk about how to take notes, how to search information on the internet, how to get what you want from the internet, that kind of stuff. And origins. So like yeah, I like very fought my urge when I was writing this thing. I wanted to explain on each of these things, but like because time, because crunch of the time, probably not this time. So like how these things, psychology and how cognitive sciences relate to this, and I thought of like linking resources to computational thinking. There's a great online course from MIT. It's called Computational Thinking in Julia. It's by, I don't know if you guys follow this YouTuber called Three Blue One Brown. He puts great YouTube videos on mathematics. So he's the professor there. He teaches, right? It's great. So I'll share those resources later. And yeah, and like this thing is the making this idea concrete by bottom of whatever we discuss. These things we will be implementing in the programming sessions. So we will be able to actually see these things in action when we do the intro to programming sessions. So I think that was all for my sessions. So I'll take questions if anybody has any questions, and if not, I will probably end this. Let me know. Waiting for questions, if any. Yeah, yeah. Thank you, Sanjan. So I guess that was all the session for today. I mean, I'm not sure if there is a session after this. So uh, great to see everyone here. Thank you for attending the session, and I'll see you later. Thank you, everyone.
Thank you,
Yeah,
sir. Good
yeah.
night.
Thank you, Ritesh. Thank you very much. It was very informative and interesting lecture. So, and maybe another two lectures we have, na? So, thank you.
Yeah. Thank you, everyone.
Thank you.
Bye.
Thank you. Thank you, sir. Thank you.
Thank you.
Thank you, sir. Bye.
Bye bye.
Good night, sir.
हम में है उजाला अंधियारा मिटाने का, हम में है हौसला नई उमंग बनाने का, हम में है एक जोश हर मंजिल पाने का, हम में है एक जज्बा हर जिंदगी सजाने का, हम में है जोश हर मंजिल को पाने का, हम में है एक वादा एक सुनहरा कल बनाने का, हम हैं जिंदगी, हम हैं हर खुशी,
हम हैं वो रोशनी जो बनाए आपका भविष्य और उज्जवल। हम हैं ONGC।